One way of thinking about this is that there's degrees of hardness of different kinds of problems. Kind of like rocks, if you've ever studied rocks. There's a scale for how hard a rock is. Well, there's kind of a scale for how hard problems are as well. And some of the entries on the scale include things like, well, some problems are actually not computable. We can define a problem and we can show that there is no computer program that can actually solve that problem. That's hard. In some sense, that's maybe as hard as you can imagine. An example of a problem in this class is the halting problem. And you can see I have a music video about the halting problem if you want to take a look at it, but we're not going to talk about it more in this class. There are some other problems, like I mentioned before, that are computable. We can actually solve them with a computer program, but they require at least exponential time. I mentioned generalized checkers as an example of that. There's problems that are computable and can be solved in polynomial time, like the shortest path problem with Dijkstra's algorithm. And some that are computable can be solved really quickly in linear time. The same amount of time it would take to just look at the example, you can actually get an answer. So graph connectivity is an example of a problem in that class. So what we're going to, the way we think about this is the hardness of a problem, like how connected are two nodes in a graph, or are two nodes in a graph connected. The hardness of the problem is the running time of the very best possible algorithm for that problem. For some problems, we're not exactly sure how hard they are, but we have lower bounds and upper bounds. So, for example, we might know that a certain problem requires at least n squared time to solve, but we know that it requires no more than n to the fifth. So the true complexity, the true hardness of this problem is somewhere between those two bounds. So here's a question for you. What's a good way to find an upper bound on a problem's hardness? If we know an upper bound and a lower bound, that gives us a sense of how hard the problem is. How do we find an upper bound? So here's some choices. One is devise an algorithm to solve the problem, run it on a bunch of inputs, and then look on the graph to see what the shape of it is, and that tells us the bound. So that's one choice. Another choice is, again, devise an algorithm to solve it, run that algorithm on all possible inputs, and take a look at the running time that results from this. That gives you the upper bound. Third, you can imagine devising an algorithm to solve the problem and then analyzing it, and whatever the big O or big theta is that you get from that analysis is an upper bound on the hardness of the problem. And then the final choice is, this is a trick question. The whole question of upper bounds must be some other class because it's not what we've been studying in this class. So decide which one you think is most appropriate and check it off.